Walid Najjar. He received his BE in electrical engineering from AUB in '79, and the master's degree, Ph.D. degree in computer engineering from University of Southern California in '85 and '88. And he was a professor in the Department of Computer Science at Colorado State University from '89 to 2000, when he moved to the Department of Computer Science and Engineering at the University of California at Riverside, where he is now a professor. His research interests are in the fields of computer architecture and compiler optimizations, embedded systems, and sensor networks. Lately, he has been very active in the area of compilation for FPGA-based code acceleration and reconfigurable computing. He has received many grants from NSF, DARPA, and industry. And he serves as an associate editor of the IEEE Transaction on Computers, Parallel Computing, and IEEE Computer Architecture Letters. And he has served on the program committees of a number of leading conferences in his field. And he's a fellow of the IEEE and the AAAS. So it is my pleasure to welcome Walid to his home here. So he is going to talk about what he knows best, is reconfigurable hardware accelerators, emergence of a new computing paradigm. Walid, the floor is yours.
I'm going to start with a brief history of computing. The history of computing is very short, so the brief history of computing is even shorter. There was a time where computers had to break for lunch. Okay, you don't believe me? Here they are. These ladies were called computers. That was between the Civil War and World War II. There was a profession called computers. Started being mostly man. In World War II, it was exclusively women, because the men were on the front fighting. And what these women were doing is calculating, filling up tables that did ballistic trajectories and things like that. And very much like our computers today, they would be given a formula, and somebody would bring them a set of data, and they would compute the formula on that data, and fill up another set of data, and move it to the next person who computed another formula, and so on and so forth. So it was also parallel processing. Okay. It was a very well-paid profession, by the way, because it had a lot of requirements that I know myself and many people I know would not excel at. Patience, attention to details, and perseverance. Then, the real computing, as we know it, where it started, is there. It's dark, it's big, and crowded, and lots of components. And this was the ENIAC, built at University of Pennsylvania in 1948, the first electronic computer. 17,000 vacuum tubes, 7,200 crystal diodes. The part that I like the most, 5 million hand-soldered joints. Ziad, that would be a trip. Right? 27 tons, 150 kilowatt, could do 5,000 additions per second, 1,000 times faster than anything before it. And now, this is the part that gets interesting. The ENIAC 1, the first instance of it, was a wired program. Wired program means that the program was in the switches and wires. To develop the program on paper took weeks. Then to load it into the computer by plugging wires and setting switches took several days. And to test it by single-stepping it took several days. And it was 1,000 times faster than anything up to then. The machine was up on average 50% of the time. The other 50% they had to replace something that burned. Took about 15 minutes to half an hour to fix a problem every time. In 1948, shortly after the installation, a mathematician at Princeton Institute for Advanced Studies, John von Neumann, Nemi Gray from Hungary, came up with the idea to modify the ENIAC. So instead of having the program being in wires and switches, he said, why don't we store the program in a memory? Okay, and so the memory, the processor would fetch the instructions and the data from the memory. It reduced the speed of the ENIAC by a factor of 6. Eliminated all parallel operations. They reduced the programming time from weeks to hours. Okay, this was the start of what's called the stored program or von Neumann model. Later, in the 90s, we discovered that the Colossus, which was a machine that was built by the British during World War II to break the German cipher, used the stored program also, but until the 1990s, this was 50 years after it was built, where they declassified it. It was thought that the ENIAC was the first and only stored program computer at that time. The lessons from day one, which is very important, is the importance of programmability. Okay. No matter how good it is, if you can't program it, it's useless, even at the cost of speed. Right. So we'll come back to that later. Previous automatic computers, there's a whole bunch of them here. That's not what I meant. Okay. The Zeus in Germany, what here this says, this is if it's binary or decimal, and if it's electromechanical or electronic. Okay. The ENIAC was electronic. The Manchester, baby Manchester, was also an electronic stored program, but was extremely small. Okay, this is why it was called the baby. And the last column indicates whether it was Turing complete or not. Turing complete is a short, quick definition for something that a computer is Turing complete. If it is Turing complete, it can compute any mathematical function. Okay. And there are a lot of computers that, and still are a lot of computers that are not Turing complete, and we do not need every computer to be Turing complete. I mean, Ziad doesn't need every controller to be Turing complete. Right? So the stored program model, essentially we have a memory that holds the program and the data, and the processor that fetches the instructions, which are the commands of what it should do. And then it has a bus that takes the data back and forth, which are instructions and data, and the address. So this one holds the program and data, execute fixed set of commands, and this provided the stable platform upon which the computer revolution that we've witnessed in the last 50 years has been built, because this is the common paradigm that is common to everything. And so this is the standard that enabled everything. There's on one side the software, on the other side the hardware, and everything goes through that interface implicitly or explicitly. The operating system, the languages, the compiler, the application, the architecture, the microarchitecture, and the technology. Okay. You can change languages. It still talks the von Neumann paradigm. You can change operating system. You can use Windows, Linux, everything. You can change technology from TTL to CMOS and all of these things. It is the fixed point and the standard. And because of that, we have seen what we have seen over the last 50 years. However, standards have to be kept and gone beyond. Okay. The standard that enabled the Industrial Revolution was the steam engine. Okay. Luckily, we don't have any more steam engines. Okay. Nobody's shoveling coal. Now, the other thing that happened in the last 50 years is the well-known, famous, now infamous Moore's Law. And this is the transistor count from 1971 to 2008. Tremendous, this is logarithmic scale, of course, over time. And this was first observed by Gordon Moore, co-founder of Intel, with Robert Noyce, in a 1965 paper while still at Fairchild. Both were at Fairchild, left Fairchild, because Fairchild was not interested in this, what do you call it, microprocessor kind of thing? Yeah. Exotic stuff. No, we want to do cameras. Okay. You know, everybody buys Fairchild cameras now, right? Corollary of Moore's Law is that we have had for many years performance doubling every 2 months, every 18 months, every 2 years, year and a half. Smaller transistors, more transistor per area, faster switching speed, larger dies, more logic per chip, sophisticated micro architectures, and better compilers. Fast forward to the present. We're witnessing an era of, as a matter of fact, The Economist a couple of months ago had a special technology section, large technology section about this topic. People call it information revolution, or people call it data explosion. Data explosion means that it's all junk. Information. So the difference is, and people are still debating what's the difference between information and data. We'll get to it. But essentially, this phone here is more powerful than a Cray 1, okay, when it was first built, right? It fits in my pocket, right? So we have pocket-sized supercomputers, terabytes networks, terabytes per second. In 2013, the internet traffic is expected to be 667 exabyte, 10 to the 18. This is many orders of magnitude the US Library of Congress. Data generation rate today, and this gap is growing exponentially, is twice the total available storage worldwide. Every year, we produce more data than we can fit on all the disks in the world. Start deleting, guys. 4.6 billion cell phone number subscriptions in the world out of 6.8 billion people. Okay. Nokia, I think, still sells about 1.1 million cell phones a day. And they have a they're still the largest, but shrinking. 1 to 2 billion internet users worldwide. Some people say information is data plus analysis. Okay. How are we going to do this analysis at such massive amount of data? What does it mean? How can we do it? Do we have even the storage to put the data to analyze it? Back to the future. Why not go back to circuit-based computing, like the first ENIAC, before Dr. von Neumann had a chance to mess with it? Okay. Not the vacuum tubes and all, but the idea. ASICs do computation by circuits, but they're not reprogrammable. Okay. And they're expensive. FPGAs are chips that can be programmed by software, but that model was called the fixed plus variable, have a CPU, and have a fabric of configurable circuits next to the CPU. The other problem we face today with processing all this data is the memory offloading problem. Let's say I have data coming from a data source, a pipe, that would go through some kind of a DMA, direct memory access, that would take the data and will put it in a memory. It has to go to a memory for the CPU and the von Neumann model to be able to do anything with it, right? So the latency of the memory in today's CPUs is millions of CPU clock cycles, because memory is very slow. So the latency becomes huge. Plus, if the data does not fit in the memory, we have to go to disk, the latency is even bigger. So limited throughput, high energy consumption. The solution is to have an FPGA through which you can stream the data, and it does the analysis on the fly at line speed. So this fixed plus variable model can be implemented, something like that, where I have a CPU that will configure the FPGA, the data comes to the FPGA does the analysis at line speed, and then will put the results in the memory. Okay. What kind of applications would benefit from this kind of a model? Any application with large amount of streaming data. Signal, video, image processing, network intrusion detection, databases, data analysis, data mining, bioinformatics, computational chemistry, tons of applications like this. We can have hundreds of concurrently operating floating point operations on a single FPGA running at over 300 megahertz, sometimes 500 megahertz, some devices, so 30 gigaflop. And if you transform that into fixed point operation, which is one of my pet peeves, that floating point is very much misused and abused, and most of the time useless, okay, because it's not associative, if you remember what associative is. Okay. And so basically, we're looking at three modes of computation in software, in hardware, and reconfigurable, where the advantage of one or the other are obvious: speed, flexibility, programmability. The drawback of FPGAs is that they're not easily programmable. One has to know VHDL or Verilog to program them. And the advantage is that the performance compared to CPU goes from the 10x to 10,000x in these types of applications that I've mentioned. But the programmability is very difficult. So this is where I started working about 12 years ago on this type of problems. And about 6 years ago, we started on this project, Riverside Optimizing Compiler for Configurable Computing. And this to address the programmability of FPGAs. And the idea is to make them programmable from C down to the circuit level for people who are not hardware designers, who are not trained at AUB, ECE definitely, and who are Joe Blow programmer who knows C, right? And so this is a joint project at UC Riverside, and we have with my students a small startup called Jacquard Computing, and it's a free and open source product. So as he had said, we're not concerned about where we're going to make money. We're doing something that is useful, we think, and money will come. And we have a contract at the company with the Air Force. And this is a quick snapshot of the GUI that's implemented with the ROCCC compilers. And one of the big strengths of the compiler is the extensive set of optimizations that it can implement that are unique to it. The results, this is relatively recent. We compare to how does it compare to a good programmer programming in VHDL. So in the clock frequency, we are higher clock frequency on average than the VHDL program. The throughput, we're also higher. Area-wise, we're larger. We use more area. And that's understandable because we do better pipelining. This is another result, still working on the paper. It's going to be submitted tomorrow. We show that we do much better pipelining than the best synthesis tool available. The productivity, this is the part where we're much better. It's 4 times better productivity. Productivity is measured in lines of program per lines of program, and we're 4 times. So looking ahead, and I say foolishly because anybody who predicted the future in this business turned out to be a fool. Nobody succeeded. So, but it's always good to look ahead. Planes, trains, and automobiles, of course, is a famous movie, but what I mean by this is we have more than one paradigm for transportation. We've had an excellent paradigm for computing that took us through the past 50 years and made everything possible. But now it's time to start investigating other paradigms because that suit is getting too small. Okay. And of course, bicycles, skateboards, and rollerblades. Anybody, I don't know, here I didn't see much at AUB, but on the campus where I am, it's always you have to dodge the guys coming on skateboards because, you know, you lose, it's not allowed. If you collide with that guy, you're on the losing end. I mean, there's no... Anyway, so the other important development that is related and important to be mentioned, virtualization and abstraction. We're moving to location agnostic computing. The buzzword of that is cloud, but cloud means whatever whoever's trying to sell you something wants it to mean. But essentially it means your data could be someplace, your processor could be somewhere else because the speed is incredibly fast, and you're getting the result in a third place. So you start your program, and your program is to analyze some massive amount of DNA data, and that DNA data is on a database somewhere, but your program is running on a supercomputer somewhere that's probably distributed over many nodes, okay, geographically distributed, and you're getting the result here at AUB, right? So what do you have? You just have the bits coming on your screen. And the other thing is, we still do, our programming tells the computer how to do things, okay? When we write the program, we're telling the computer how to do it. What we're moving towards is programming paradigms where we tell the computer what to do, and the computer will figure out how to do it based on the resources available and the type of data that we're, right? Okay. So matrix inversion. Okay, let me do the matrix inversion. Don't tell me how to do it. You don't go to the restaurant and then go to the chef and say, now you flip the meat now, please. You know? Okay. But we needed that because computers were at the very beginning, right? Now, when we get to the point where we tell the computer what to do, we can have programming paradigms that are mathematically sound. I equal I plus 1 does not make sense mathematically, right? There's no such variable. Okay. And when we get to, do you know of an I equal I plus 1? It's a location, right? Yeah. When we get to statements, programming statements that are mathematically sound, then we can get to verifiable programs that you can prove correct. Wow. That would be the day. I mean, security would be fantastic. Okay. That's it. Thank you.